This is the presentation about the policy gradient. These are the contents. First, I'll explain basic concepts and motivation of policy optimization. Second, I'll show you how to estimate a policy with likelihood ratio gradient. And finally, I'll introduce some techniques to reduce variance of the estimate. So, the introduction. To begin with, we revisit the reinforcement learning landscape. Up to now, we have covered dynamic programming, which includes policy iteration, value iteration, along with Q-learning. Today, we will move on to policy optimization, especially policy gradients. Then, we'll introduce actor-critic methods, combining policy gradients and dynamic programming. This is the basic setup for policy optimization. We consider that the agent has a policy parameterized by theta. The theta can be any parameter of function, like simple linear to neural network shown here. When h denotes the horizon, our goal is to maximize the expectation of the sum of the rewards given the policy over h. Here, we set our policy pi to be stochastic, which means that we have distribution of actions in every state. For deterministic cases, like grid world, the choice of action may change dramatically for an arbitrary small change in the estimated action values. However, with policy gradient, we slightly change the distribution. It will slightly shift the expected sum of rewards. Then, the optimization problem smooths out, and now we can apply gradient descent. So, why policy optimization? There are several reasons. First, often setting policy pi can be simpler than setting q or v values. As an example, let's consider a robotic arm grasps a stick. To learn q or v values, we need exact numerical reward associated with the process, which might be the timing or how robust the grasp is. It is difficult, but if we use policy optimization, we can just skip these details. Second, for the calculation of v-values, we need the dynamic model to understand what action we should take in the current state, as shown in this value iteration equation. However, for policy gradient, we don't need the dynamic model, and it will be explained later. Finally, it is tricky to solve argmax q. Especially for continuous or high-dimensional action spaces, we cannot have one possible output per possible action because there are infinitely many actions we will take. Let's make a comparison between policy optimization and dynamic programming. Conceptually, policy optimization directly optimizes what we care about, which is the policy. Dynamic programming first calculates v or q values to find the policy, which is indirect. Empirically, as we can set up policy with various functions like neural network or linear functions, policy gradient is more compatible with rich architectures and more versatile. And for dynamic programming, by using off policy, which can refer to policies other than current policy, it becomes more compatible with exploration. Also, dynamic programming looks more detailed to the problem by evaluating not only policies but also q or v values and can use data more efficiently. So, the method we will use for the policy gradient is called the likelihood ratio gradient estimate. Let's denote tau to be a state action sequences over the horizon h. Then we will associate the reward with the entire state and action sequences, and the notation is given here. Also, we define utility u, parameterized by theta, as an expected sum of rewards. We can write this as the sum of paths times the reward, where path p indicates the probability of state and action sequences times the reward at the state and action sequences. Our goal here is to find the theta that maximizes the utility function, and for this we apply gradient ascent, just like we've done gradient descent to find hypothesis that minimizes loss function. We'll go through some mathematics for better understanding of the algorithm. We defined u before and as we try to apply the gradient ascent, we need to calculate the gradient of u with regards to theta. The first equality comes from the definition of u, and the second one is by Leibniz integral rule, which implies that the gradient and sigma sum can switch their position. For the third equality, we apply a simple trick which is usually called the probabilistic identity trick. For the fifth equality, we use the property of the gradient of log, and the final equality is by the definition of expectation. Immediate implication of the equation is that we can approximate the gradient with the empirical estimates for m sample paths under policy pi theta. Let's briefly see what the likelihood ratio policy gradient does graphically. There are m equals 3 paths shown, and each of them has good, which is positive, medium, and bad, which is negative rewards. Here, gradient tries to increase the probability of paths with positive r and decrease the probability of paths with negative r. Also, note here that the gradient of utility function depends on the sampled trajectories. It is going to have high variance depending on the path it takes. This high variance is a major problem of policy gradient, and we'll cover it in next section. Before that, let's do some more math for the simplification of the equation. Previously, I have mentioned that the policy gradient does not need dynamics model for calculation. Here comes the derivation by decomposing paths P into states and actions. It can be shown graphically like this. By dynamics model, we change state to st given previous state and action, which is st-1 and ut-1. Then by multiplying policy, we move on from state st to action ut. As we keep moving on, multiplying this calculation for the horizon would give us the probability of the path along the horizon, which is p. Then by definition, it can be expressed like this. By the characteristic of log to change multiplication into sum, the second equality holds, and as dynamics model is not dependent on theta, the third equality holds. Therefore, the grad log p can be equated by the sum of grad log policy. Combining equations we covered until here, an estimate of the gradient, which is g hat, has a form like this. And we should also check that the estimate of the gradient is unbiased by law of large numbers, which means that it can be a useful estimate. Now, let's change our focus to the problem of the policy gradient. Because the process is mainly done by sampling, it has a high variance. In this section, I introduced how to reduce the variance of gradient estimate. The first method is an idea of considering a baseline b. Here, we multiply r minus b instead of r with grad log path in the equation of the gradient of the utility function. So there are two questions here. What if the bias changes? And does it really reduce its variance? Here's the answer for the bias part. If we consider the added part of the equation and b not dependent on action, then b comes out of the sigma sum, and as the sum of all paths is 1, the gradient of it is 0. Therefore, we can be sure that the bias does not change. So, for the question of whether the baseline really reduces the variance, we prepared an intuitive example. We considered 3 paths, and each grad log path and reward has following values. Comparing the results with and without baseline, we can see significant changes. Here's mathematical approach to the baseline, and it is called a control variate. The basic setting is for the given distribution x, random variable c, some constant b, and we want to reduce the variance of newly corrected distribution y. The relations is like this, and c minus expectation of c is called a control variate. First, for the expectation, we can see that the expectation of y and x are same. Also, considering the variance, we can write the variance of y with the variance and the covariance of x and c. So, if we say this equation becomes greater than 0, the variance of y is reduced from the variance of x. If we think this application, we can understand why the use of baseline can reduce the variance. There's another method called temper structure to reduce the variance. We know that, in general, removing terms that do not depend on the current action can reduce variance. So we deploy the gradient of the utility function as follows. Here we find out that there exists a term that indicates the sum of the rewards before time step t. Considering Markov, the past reward does not affect the current action and only future reward affects, so we can remove the term and reduce the variance. Back to baseline, there are several choices of baselines, simply from constant baseline to mathematically optimal constant baseline, and etc. However, what we usually use is the state-dependent expected return, which is just the optimal value function. This is because the value function tells how much reward we are gonna get from the state onwards. So, let's see how we can estimate the optimal value function, and there are two methods. So, this is the first one. According to previous lectures, given dynamic models, we can use value iteration to calculate optimal value function. However, in policy gradient, we didn't assume dynamic models. Therefore, we just set the value function to be parameterized by phi and collect all the samples. We change it to a regression problem and minimize the value function. And this is the second method. Bellman equation for the value function is given as follows, which divides the value function from current state to the immediate reward plus the value function afterwards. So, we set the target value to be the sum of the immediate reward plus the value function afterwards, and for each time step, we perform gradient descent to minimize the value function. This term with lambda is regularization term for the better results. Combining up to this, we present vanilla policy gradient. So, we first initialize policy parameter and the baseline. During the iteration, we collect trajectory samples and each time step, calculate the reward and reward minus the baseline. This follows the first way of estimating the value function. We refit the baseline with the information and update the policy by the likelihood ratio gradient estimate. Now, let's recall here our likelihood ratio policy gradient estimator. This term, the sum of the rewards, can actually be viewed as an action value function, which is Q. Estimation of Q from single rollouts like this also gives us high variance. Therefore, we use discounting gamma or function approximation to reduce the variance. So the top equation is an action value function with discount factor. For the function approximation, there are widely two researches. One is asynchronous advantage actor critic, which can be shortened as A3C, which decides some case steps for the approximation of Q. And the other is generalized advantage estimation, which is GAE, which uses some lambda and take exponentially weighted average to approximate Q. In short, we reviewed policy optimization, how policy gradient works, and how to fix the problem of high variance. This model, actor critic with asynchronous advantage actor critic or generalized advantage estimation, combines all the concepts and algorithms we have covered. And there are still many variations ongoing to reduce the variance and utilize the policy gradient more wisely. So this is the end of the presentation. Thank you.